So other is called a liquid to liquid, or where phase change happens. So based on this definition of beta, if the number is 400, so that then if beta is greater than 400, we call it a compact heat exchanger. In the case of liquid to liquid heat exchanger type or phase change type. So we'll start with one very primitive example just to get started, and so that we can break the ice between you and me. I'll encourage you to give answers in comment box, or you can unmute and answer to me. The first question, you have it on your screen. For a given heat exchanger, the value of heat capacity ratio is, that is defined by R. The heat capacity ratio is the ratio of the specific heat of the hot fluid to the cold fluid. So what is the extreme, what is the range of this R value? That's what the first question is. Can you people just answer it? It will be better if you can unmute yourself and talk, because I have to come back to the Google Meet screen.
Sir, answer should be A, 1.
Okay, one of your friends says it is A, and some other in the chat box I have it is D. So it is equal to 1. One of your friends says it is equal to 1, and one of your other friends says it has a range between 0 to 1, both 0 and 1 included. Does anyone want to answer this? You can join.
It should be D.
Okay. Can you give cases where R equals 0 and R equals 1? Do you have any examples, or do you have any idea in your mind that for this case R equals 1 and for this case R equals 0?
Sir?
Yeah.
I think I might, I guess when R equal to 0, it means that like the denominator is almost infinite. Like in the case of condensation,
Okay.
which I understand, where the like vapor condensation, so the vapor temperature is actually not increasing. So in a
Okay.
way, we can say that the specific heat of the vapor is almost infinite.
Okay.
And so it's
Okay.
something
For the case of R equals 1?
R equals to 0.
Yeah, R equals 0, what you have said is right. Do you have something to share with us on R equals 1?
R equals 1. So maybe we are using the same fluid only. I'm not sure.
Okay. What your friend is saying is, we have the definition of R as Cp of hot fluid to the Cp of cold fluid. Cp is specific heat at constant pressure. So when there is a phase change, I'll take my cursor here. Okay. So we are familiar with T versus S graph of a vapor compression refrigeration system. So here we have a compression, then we have a condensation, then we have expansion in the throttle, and again we have an evaporation process. Okay, so it is not necessary that we need to know about this cycle, but this is one of the most famous cycles, so I give this example. So I am more interested in this part now, the place where I encircle. So this is called a condensation portion, and this is called boiling portion. So the refrigerant or the thermodynamic working fluid is undergoing a phase change from superheated state, that is it is completely in vapor state, and inside this dome this is in liquid plus vapor state. That means a part of refrigerant is in liquid, a part of refrigerant is in vapor. So in this case, the Cp is defined as dou H by dou T at constant pressure. At constant pressure, for a change in enthalpy, what is the change in temperature? So Cp, I will just recollect for the benefit of the class, dou H by dou T at constant pressure. So this is a constant pressure condensation. So we are in this variable is fine. What is the change in enthalpy with respect to change in temperature? So when it undergoes a condensation process, or similarly for boiling process too, there is no change in temperature for a pure fluid, and for a specific change in enthalpy. So that's the reason the denominator becomes 0 and Cp becomes infinite. So in this case, R becomes 0. So this value of it is satisfied. So for other cases where this is one extreme case that I have discussed, that R to be 0. But in case we consider the heat exchanger to be here, only in this portion, that means Cp of hot fluid and Cp of cold fluid have certain values. None of them is infinite and none of them is 0. So as a result, what we get is we have certain value of R, but because Cp of hot fluid will be more than the Cp of cold fluid, we have it less than 1. And in the case of regenerators, I have already explained it to you how a regenerator works. We have a tube which is stacked with high heat capacity material. That means why high heat capacity? The reason is it should be able to absorb more amount of heat. It needs to store more amount of heat within itself. So the hot fluid passes in one cycle. The hot fluid gives some part of heat to this material inside the tube, and the hot fluid ceases to pass. The first cycle is done. Now on the same balls or the same material, the cold fluid again passes in this fashion. We need to remember that both these fluids are not mixing. They have certain other arrangements at the end. So the cold fluid passes here, and for the regenerator R equals 1. So the correct option is D, where the heat capacity ratio ranges from 0 to 1. It is not equal to 0, it's not equal to 1. And obviously it can't go to minus. So if R cannot be less than 0, because it's the ratio of two positive quantities, Cp can never be negative. So the option C can straight away be ruled out. So the remaining option is D, 0 to 1. Okay. We have another question here. You can look into the statements given 1, 2, 3, 4, and which of the following statements can be true about heat exchange, are true about heat exchangers. First one is LMTD of a cross flow heat exchanger is some correction factor times LMTD of a counter flow. LMTD, as we know, it is logarithmic mean temperature difference. For heat exchangers, the LMTD method is one of the most significant methods to size or rate heat exchangers, which we are going to learn in our next classes, next video sessions. So the first statement is that. The second statement says the inlet temperature of a cold fluid can be more than the exit temperature of the hot fluid for a parallel flow heat exchanger. So can you go through and give your answers? Which one do you think it is correct and which one is wrong?
That should be D.
Okay. One of your friends says the option D is correct, that LMTD of a counter flow should be greater than cross flow and parallel flow. Uh, are there any other statements which can be true?
I think the first option A also.
Okay.
Uh, yeah, first option.
Yeah. Uh, your friends have given correct answers. They have picked option A and D. Yes, both of them are right. LMTD of cross flow heat exchangers, what we write as Q equals UA into some factor F, that's the correction factor, into LMTD. For a counter flow heat exchanger, this factor is 1, and so we do not take, so the most general one that we tell is Q equals UA LMTD, but it's actually UA. For cross flow heat exchanger, it becomes UA into some correction factor times LMTD. So the first statement which says the cross flow heat exchanger LMTD is some correction factor times counter flow, that is correct. The second statement, the inlet temperature of cold fluid can be more than that of the exit temperature of the hot fluid. No, this can't be correct in any heat exchanger, because the cold fluid temperature, if it were to be greater than the exit temperature of the hot fluid, in the case of parallel flow, there will be crossovers. So it can't happen. The third one, counter flow heat exchanger is least efficient when one of the fluid changes its phase. Uh, Next week we are going to learn in the theory classes that the expression of effectiveness and NTU. Effectiveness is denoted by epsilon, and NTU means the number of transfer units. EXP means the exponential function, and C star is the ratio of heat capacities. We'll find few expressions for effectiveness and NTU for different arrangements. Like I have told you that there can be cross flow arrangement, counter flow arrangement, and a parallel flow arrangement. Parallel flow is the one where I can show you in this fashion. Parallel flow is the one where hot fluid and the cold. Assume that we have two concentric tubes, one inside the other. Inside first tube has say hot fluid, and the other tube or the outer tube has a cold fluid, and both of them pass in the same direction. Such kind of a configuration is called a parallel flow heat exchanger. In case the hot fluid is in positive x direction and the corresponding or interacting cold fluid is in opposite direction or 180 degree out of phase, then we say that this is in a parallel counter flow heat exchanger. We have certain other cases like uh, air cooled heat exchangers, where the path of hot fluid is in positive x, if we can say, and the path of cold fluid is in positive y, or you can say negative y. So there is 90-degree angle between the hot and cold fluid. So in these three configurations and many more configurations, we are going to learn the effectiveness NTU relationships. Why I have told you about this parallel, counter, and cross flow is for different NTU, for different arrangements, the effectiveness and NTU relations are different. So I just wanted to ensure that that point is also stressed upon. So coming back to our problem, counter flow heat exchanger is least efficient when one of the fluid changes its phase. So when one of the fluid is changing its phase, that means C star becomes 0, but we cannot say that the effectiveness is least at that position, because it also depends upon one more factor called NTU. NTU is defined as number of transfer units, elaborated as number of transfer units, and it is expressed as UA by m dot Cp, m dot Cp of the minimum That means we need to take that fluid which has m dot Cp minimum. We have two fluids here, hot and cold fluid. So the denominator is the one corresponding to the fluid which has least m dot Cp. UA is overall heat transfer coefficient multiplied with the heat exchanger surface area. Okay. So the third one is also not a general statement, so we cannot say even this. The fourth one, for the same inlet and outlet temperature of hot and cold fluid, this is a well-known fact. Or else, to justify this, we can take few numerical or general temperatures and check whether LMTD of counter flow is greater or cross flow is greater. So even D comes out to be true. So the LMTD of counter flow is greatest, followed by the cross flow and then the parallel flow. So both A and D are to be correct. So we have multiple answers here. I just want to again stress upon the classification of heat exchangers. That's why I have given this, taken up this example again, so that we are sure with the classification that is discussed. So can you unmute yourself and tell me which one is boiler and condenser that fits into the classification? Any answers?
D should be D, sir. Direct transfer type, multi-phase heat
Okay.
exchanger.
Yeah, I have one answer. One of your friends says that boiler and condenser fits into the class of direct transfer type multi-phase heat exchanger. So that is right. We'll define what, we'll recollect what direct and indirect contact type heat exchangers are. I have already stressed this, but once again, the direct contact heat exchangers are where the two fluids mix with each other. That in case of cooling towers, both the hot and cold fluids mix. So that's called a direct contact heat exchanger. Indirect contact heat exchangers are the ones where fluids do not mix with each other. Best example that we can practically see is our home refrigerator. The refrigerator inside or the thermodynamic fluid inside does not come into contact with the atmosphere or any other fluid. So that's called an indirect type contact heat exchanger. Even even our commercial home ACs too. So the correct answer is D. Also, yeah, as I have shown you here in our Rankine cycle, that there
Sir,
is,
one second.
yeah,
Sir, can you just go to the last slide, please?
yes,
Yes. Sir, are you talking about the reboiler and condenser?
yeah. You can take a general boiler and a general condenser. You can,
Then in case of reboiler, suppose we have distillation column and we have thermosyphonic reboiler, then generally we used to use steam in that side, tube side, sorry, cell side, and the
mm,
tube side is that hydrocarbon, which is maybe the forced circulation or maybe that thermosyphon reboiler.
okay,
Sir, in that case, both fluids are not mixed together, but it can be that our based on the evaporation rate, our tube side fluid can be 5% vapor, maybe even can be 40% vapor,
mm,
and that outlet steam, the inlet cell side steam, we are putting steam, right? It is in
mm,
the phase of vapor, and we are that can be collected as a condensate.
mm,
So in both case, it is a indirect contact, but multi-phase is possible because in for the tube side, it can be completely liquid to partially vapor and liquid,
mm.
and for cell side from vapor to liquid. So is it like so? And because that direct contact type, it is not kind of direct contact type.
It is indirect only.
we need to come back to the options once again. Direct transfer type multi-phase heat exchanger. Okay, okay. We have to reframe this question to uh, fit into this. Fine, fine, fine. Okay, we'll discuss again about this.
Sure, sir. Maybe
Yeah,
it's okay. Thank you.
yeah, yeah. We need to modify this in order to classify it again.
Yes,
Yes,
yes.
we will
Fine.
do it.
Sure, sir.
Yeah,
Thank you. Thank you.
yeah. We will, for the time being, we will just skip that question. We need to have more constraints on the question to classify it, which we'll do later. So I have one more question for us. Uh, for a given heat exchanger, let us assume that we have delta T max, delta T min between two fluids. LMTD is a logarithmic mean temperature. We know Cmax and Cmin. So, what is the maximum heat transfer that can be possible between these two fluids? Uh, some of us might be knowing already the direct final answer, but for different cases of CH being greater than C cold, uh, I encourage you all to work out and tell me.
Sir, I can say that as per the literature, it should be C max delta T mean, but I need to check that exact calculation if I'm not wrong.
Okay,
I think it's the B option, C mean times the delta T max.
okay. Two of our friends say C max into delta T min. Other friend says C min into delta T max. So, any other answers?
C max delta T max.
Okay.
C option.
Okay, we have two answers predominantly. One is C min into delta T max, and the other is C max into delta T min. C max into delta T max. Okay, fine.
Yeah, it could be in between C or D, not A and B.
Okay, fine. So let's start from the basics. How we calculate maximum heat transfer rate that is possible between two fluids. So assume that we have for maximum heat transfer to happen, we'll assume that we have a counterflow heat exchanger which has an infinite surface area. Why only counterflow? We can do it for other configurations also, but to take a case and work it out, I have taken a counterflow heat exchanger. Okay, so TH in and THO are inlet and exit, TCI and TCO are inlet and exit of the cold fluid temperatures. So subscript H is hot, C is for cold. So the heat transfer between the hot and cold fluid can be written as CH. M dot CH we have to write, but M dot is absorbed into CH. Okay, so we can write it as Q is CH into delta T of hot fluid, that is heat lost. The same heat is also being gained by the cold fluid, so it can be written as Cc into delta T of cold fluid. I hope there are no objections with this, because this is conservation of energy. Heat lost by hot fluid should be equal to the heat gained by cold fluid. So we'll take different cases of fluids where heat transfer happens. For the example where hot fluid heat capacity is more than cold fluid heat capacity, we have for a particular Q, when CH is less than CC, we have THI minus THO. This quantity THI minus THO should be greater than TCO minus TCI. Okay, so that is for this case. Because we have taken an infinite length heat exchanger, TH exit and TC in match, and TCI and TCO have some particular delta T. Okay, so we'll write the expression of Q max that is possible now in this case. Remember this, the first one is for on this graph it is for CH greater than CC. This one corresponds to CH less than CC. So Q max is nothing but C hot into delta T across this THI minus TCO. THI minus TCI. What is delta T max here? This is delta T max. THI and TCI. So it becomes CH into delta T max. What is CH here? It's our minimum heat capacity fluid. C min into delta T max. This is for first case. We'll consider second cases also. So what happens when CH equals CC equals some constant, say C? We can write our expression as Q max of CH into THI minus TCI. When the heat exchanger is of infinite length, the temperature profiles of both hot and cold fluid overlap. So this is our hot fluid, this is our cold fluid. Obviously it can't happen, but because we are considering a heat exchanger of infinite length, this is how the temperature profiles look. So the delta T max between these two is these 2 points, delta T max. So for the third case where CH is greater than CC, we write Q max as CC into what is delta T max here? This is nothing but THI minus TCI. So this is delta T max. What is CC here? It's a minimum heat capacity fluid. So as a result, the correct answer is going to be C min into delta T max. This definition is going to be extensively used while we define heat exchangers, heat exchanger effectiveness. So denominator term is going to be Q max for a particular heat exchanger. So I wanted to show you these examples. So the maximum heat transfer that is possible between two fluids in a heat exchanger is C min into delta T max, irrespective of the configuration. Are there any questions here?
No, sir. Thank you for the correction.
Yeah. Yes. Okay. We'll just go through the law of conservation of energy. It's a very basic problem now which I am going to show you. As I've told you, from next sessions onwards, once we take up effectiveness NTU methods, we'll pick up more speed. So just to get warmed up with this session, I just wanted to show you the first law application also. So I encourage you all to take up this problem and tell me the solution. I'll give you a few minutes of time. We have a counter flow heat exchanger where Cp of the hot fluid is given, the mass flow rate is given, the inlet and exit temperatures are given, the cold fluid heat capacity is given, mass flow rate is given, inlet temperature is given, the exit temperature has to be known. So you can apply the first law of thermodynamics, that heat lost by the hot fluid is equal to the heat gained by the cold fluid, and answers, or do you need some more time to work out?
Just a minute.
Okay.
Answer only C, sir, 32.5.
Okay, one of our friends says it is 32.5. I'll give you a little more time. If anyone has some more. Okay. So we have a counterflow heat exchanger where I've marked few points on the counterflow heat exchanger. Counterflow means the hot fluid and cold fluid are in opposite directions, perfectly opposite. So inlet is given. We'll take this as the hot fluid, the top one, 150 to 100, and this is given to be 20. So obviously it should be more than 20 because it will gain heat. That is by first law. So we'll try to apply first law of thermodynamics. Q lost by hot fluid should be equal to the Q gained by cold fluid. So m dot Cp of hot into T1 minus T2. So this corresponds to T1, this corresponds to T2, equals m dot Cp of that fluid, cold fluid which we are talking about. So I have written subscript C and subscript H to denote hot and cold fluids respectively. This becomes T4 minus T3. We just now have to plug in the values. M dot is 5 kg per second, Cp is 2 kilojoule per kg Kelvin, and delta T equals m dot of cold fluid, Cp of cold fluid, and this is what we want, and this is already mentioned. So this comes out to be 32.5. So obviously it should be more than 20 and less than 150. So we are in the limit. That before starting we can have just an estimate like that. Can we move forward?
Yes.
Yes, sir.
We have a composite question here. This is our last question for the day. We have a counterflow double pipe heat exchanger where water is heated from T1 to T2 by another fluid oil with Cp of so and so and mass flow rate being 0.9. The oil is cooled from 230 to 160, and we have the overall heat transfer coefficient U as 420 watt per meter square Kelvin or degree Celsius. So we have four uh, composite questions one after the other. I'll give you few minutes of time. You can work all of them and tell me the answers. Or if you find the first one, you can unmute and answer also. That's also fine.
I guess the first option, first answer rate of heat transfer would be 52.2 kilowatt.
Uh, may I know how you have calculated?
Yeah, so like I did Q equals CPC, that is the specific heat of the cold fluid, which is in this case water. So the specific heat of water times the mass flow rate of water uh, times the outlet temperature of water minus the inlet temperature of water. That is 65 minus 25.
Okay.
Okay, just a minute. I think I made a mistake. These are specific heat and mass flow rate of oil. No? Oh.
The mass flow rate of water is not given.
Okay. No. Yeah, so there's a mistake. So it would be 91.35 kilowatt.
Okay.
I have now calculated in terms of oil. So
Yeah. One of your friends says the heat transfer rate is 90 around 91.3 kilowatt. Any other answers? Okay. Now I think you can find out the mass per rate of water. People who have calculated heat transfer rate, now you can calculate mass per rate of water.
sir, will you please show the screen for the
Okay.
question?
Okay. One of our friends says mass flow rate of water is 0.546 kg per second. Is LMTD related to the efficiency of heat exchanger? Okay, I'll come back to it.
Audible?
Once people who have completed mass flow rate of water, you can try LMTD of the heat exchanger. Any answers for LMTD? I think it should be a straightforward. Now after that you reached direct temperatures.
Yes, so LMTD is 53.6 degrees Celsius.
I would suggest you to check one second.
Okay.
We are in a counterflow arrangement. So LMTD is delta T at one end minus delta T at the other end divided by ln of delta T1 by delta T2.
I did the same thing again. It's coming
Uh,
53.6.
can you check your delta T1? What is your delta T1 at hot
Again,
end?
LMTD coming 150.9.
150.9. I think you are close but not exact. But yeah. So delta T at one end is the person who was getting 59 or something. I'm just suggesting him. So delta T at one end is 230 minus 65 degrees Celsius.
Yes, sir.
Okay, so that comes out to be 165 degrees Celsius.
Okay, okay, yeah, yeah.
Sir,
Okay,
I'm getting 143.
143. Close but not exact. Wait a moment. Are you using ln in your calculator or log in your calculator?
LN.
Okay, fine. Then you should be getting around 149. Okay, maybe I'll tell you about the LMTD and then come back to part 1 and part 2 so that you'll be able to calculate surface area from LMTD. Okay, uh, just a moment. Yeah. So LMTD is nothing but I think I have written it. Yeah, delta T1 minus delta T2 divided delta T1 minus delta T2 by ln of delta T1 by delta T2. So what is delta T1? Delta T1 is the temperature difference between at this end, 230 minus 165. So we need to draw a diagram schematic at least. So because it's a counter flow, we need to be careful which one is entering and which one is leaving. So this is delta T1 in this heat exchanger. This is delta T2. Okay, so as per our definition, this is what it is: delta T1 minus delta T2 by ln. It's not log, it's not to the base 10, it's base e. So we need to use ln of delta T1 by delta T2. So in our calculators, when we write, in case we are taking log, it's going to be wrong. So I'm cautioning simple aspect. We need to take ln of delta T1 by delta T2. So we have values that it is 165 and 135. Once you plug these values in this formula, you think I think we should be able to get 149.49. Is that okay for everyone?
Yes, sir. 149.55 I got. Actually, this 165 and 135. So, how much digit you take after decimal? That give you a little bit variation in the answer.
Mm. But these are whole numbers only. I think you should not have a problem with that.
Yeah, like sir,
Uh,
165 or 135. So it is coming about 0.12222 like that. So after decimal, how many digit you take? So this small variation coming like
Okay.
150.5, 145, 49.5. Yes.
okay, you are telling about ln of 165 by 135.
Right, sir. Right, sir. Right.
Okay, fine. Is everyone comfortable with LMTD? There should not be any problem once you find delta T1 and delta T2. It's just plugging the value in this formula and getting it. So the right answer is 149.49. So the person who was telling about 50, are you comfortable?
Yes, yes, I made a mistake.
Okay, fine. That's okay. Yeah, the last part of the question, surface area of the heat exchanger. I'll give you a small hint or the direct hint. You can write Q dot as UA where U is the overall heat transfer coefficient already given to be 420. We need to find out the heat transfer surface area A into LMTD.
Yes, so it will be 1.455
Yes, correct.
decimal.
Correct. Any other answers apart from 1.45? Okay. Now that we have not bypassed this question, LMTD is straightforward. We already have temperature, so it's not nothing wrong to start with LMTD. So I did the same way. I started with LMTD while I was working out. So we'll come back to the first problem. We'll find the heat transfer rate. So heat transfer rate is nothing but Q dot. It can be written as uh, m dot of oil into Cp of oil into delta T of oil. So inlet and exit temperatures of oil are already given. So it is 230 minus 160. That will be delta T. Cp of oil is also mentioned, so we'll take it from the question itself. M dot is also given. So the rate of heat transfer is 91.35 kilowatt. Uh, can we move forward? Okay. Now to find out the mass flow rate of water, that's the second part. Right? Yeah. Now to find out the mass flow rate of water, we have from first law that heat lost by hot oil should be equal to the heat gained by cold water. So heat lost by hot oil is already calculated by us from the previous bit. It is 91.35 into 10 power minus 3 watt. So that should be equal to the mass flow rate multiplied by Cp of water. It is 4.187 into 10 cube joule per kg Kelvin into delta T of water. These values are already mentioned in our question. So m dot of water comes out to be 0.585. I'm sorry, this should be kg per second. There was a typo. I didn't write the unit properly. Is this okay for everyone? Okay.
Yes.
Okay. So next up, finding the surface area of heat exchanger. We have this formula Q dot equals UA LMTD of the heat exchanger. Uh, U is already specified in the question. It is 420 watt per meter square Kelvin. LMTD was already calculated. It is 149. Q dot was also calculated by us. It is 91.35 into 10 cube watt. So heat exchanger surface area comes out to be 1.45 meter square. Is that okay for everyone?
Sir,
Yeah. Was someone asking? Okay. Uh, we'll finish our class with this. These are the textbooks and references that are recommended for this course. For this particular session, I have read Fundamentals of Heat Exchanger Design by R.K. Shah. You can also go through this. It's a very nice book. And coming back,
this recording, uh,
yeah.
this recording will upload in the portal or no? That is that we discussed.
Do you have a website link to my YouTube channel? Because
Okay.
last time I think NPTEL was uploading on their portal. I'm not sure if NPTEL now is uploading directly on the portal or you are being given the video links.
So your YouTube link, may I know, sir, so I can go there sometimes in evening?
Yeah, I'll give it to you in the next session. Is it okay? I've recently
Yeah, okay,
created
no
it.
issue.
I
Yeah,
have
no issue.
maybe I'll put slide there also that it is my YouTube link. You can go and refer to it. I think these will be put on NPTEL channels also. Anyways, next week we'll finalize that.
Sir,
Yeah.
Okay.
I actually have a doubt in the very first question only,
Hmm.
that heat capacity ratios. Like,
Hmm.
can't it be greater? Why can't it be greater than one? Like, if the specific heat of hot fluid is more than the cold fluid.
Ah,
Not.
for knowing that, we need to know the temperature versus CP diagram of that fluid. Okay, so CP is actually material property that which depends upon temperature. So with temperature, the CP of the fluids keep increasing. So the CP of hot fluid is most for a particular pressure that I am talking. If you compare CP of hot fluid at one pressure and CP of cold fluid at another pressure, they might vary. But if you consider CP of hot fluid, CP of cold fluid, that means if you take CP of say nitrogen at 300 Kelvin and CP of nitrogen at 150 Kelvin. So CP of nitrogen at 300 Kelvin will be higher because the temperature is higher. But the word of caution here is if you take CP of nitrogen at 300 Kelvin and 20 bar, and not nitrogen, for example any other fluid, if I stress upon nitrogen, maybe it might not be true, but as a word of caution, which what I want to say is if you take CP of a particular fluid at higher pressure and CP of same fluid at a lower pressure and lower temperature, the CPs, you cannot compare the CPs. But if they are at the same pressure, CP of hot fluid is greater than CP of cold fluid. Is that okay? Is the explanation satisfactory?
Sir,
So, if the CP is greater than the CP of hot fluid is greater than the cold fluid, shouldn't it be greater than one as well? Like, R is the specific heat capacity ratio only, no? Am I correct or not?
Oh, just a minute.
also, sir, what about different types of
Hmm.
fluid, like nitrogen? Between nitrogen and oxygen, the fluids can be different too, right? So one fluid could have higher heat capacity than another.
This is actually for a same fluid.
Oh, okay.
Yeah. I'll come back to it again once again. We'll start with this, okay, in the next session. Is that okay?
Okay, fine, sir.
Yeah. Uh, and again, this one, right? Direct transfer type. Okay, okay. Fine. We are already. We have spilled the time. Next week, I'll answer to this. I have an answer. Next week we'll discuss again. Okay. I'm stopping the session. Next week we will meet at the same time. I'm happy that most of you are giving me the answers. Hope you all enjoyed it.
Thank you, sir. Thank you. See
Yes,
you
sir.
on Saturday,
Thank
sir.
you.
Thank you.
See you, sir.
Thank you, sir.
Thank you.